So to the two-sample t-test and p-value. Now for the rest of the course, we're going to go a bit rapid on the whole because we're going to repeat hypothesis testing and confidence intervals many times in all sorts of different situations. So we are going to allow ourselves to believe that you are adjusting yourselves to those concepts. Here it comes specifically in at least the first part of it. We often frame the null hypothesis by introducing a name for the difference of the two means, often called delta. D for difference, delta. And then we can test hypothesis now in a second about this difference of two means that we have a hypothesis of a specified value. The value we will often use is 0, but not exclusively. We might want to test different values, but 0 will often be used because a difference of 0 is the same as the two means being the same, right? So 0, of course, often used. And this is a statistic of the same kind as you've known now. We have the data here, right? The observed, slow down, and here we have the null, right? It's pretty obvious we should compare the observed difference with the hypothesized difference. I think it's common sense. Then, what we usually do also in statistics is to think about what is the variability of this statistic that we are looking at. And the variability of, seen as random variables, x1 bar minus x2 bar, well, you would be able to tell that to me based on the rules for variance that I taught you. Because that would be the variance of one plus variance of the other, right? And what's variance of 1? That's 1 over n1 times sigma 1 plus 1 over n2 times variance of the second. That's kind of two versions of the thing you've met previously. And now this is the theoretical expression of the variance, and here I have the plug-in version, right, where I plug in the observed variances, the sample variances from each group. So you see how this in various ways is the natural extension of what you were taught for one sample. And the reason why that is then called T-ops is because magic happens, that the T-distribution appears again. And here is the theoretical version of this result where I have the same expression, now expressed by capital letters to emphasize that I can see it as a computation that depends on the two samples. Next time I take the same or similarly two samples, this statistic will have a different value. So I should think in terms of repeatedly two samples like that. That's the sampling distribution thinking. I should have this meta way of seeing it. It follows a t-distribution, just like the single sample test statistic, t-test statistic, that's why it's called like that, of course. The t-distribution also is the right one. However, for this version of it, it looks terrible, but actually you can see it's very simple in the sense that only the two variances and the two ends is part of this formula. So even though the formula itself looks a bit terrible, it's just plugging in the two variances and the two ends, and those we have. To find the right t-distribution, that's a bit of theory behind this to realize that this is the right t-distribution to use. So it's a bit more tedious to find the right degrees of freedom in this case. And it could be non-integer even, and you could either use non-integer in your software or just round off. That's fine with me, both of it. Example. No, not example. Sorry. Here's the formal test which puts everything into the formal method. The two-sample t-test. Sometimes, when we get later on, we might sometimes emphasize the independent sample, the independent two-sample t-test. You compute the t that I just showed you by computing the means, two means, two standard deviations, put into the formula, compare with the hypothesized difference. You find the p-value. Or you do the critical value stuff. So this is a copy of last time now. It's the same as long as when you get there to the t-test statistic, everything runs the same way, right? So finding the probability of going beyond the difference I actually saw and then reject if the p-value is small, I just have to remember to use the right t-distribution, right? So I need to find out which one to use. But from that point off, it's a copy of last time. Or critical values, same as last time. That's the two sample t-test, maybe the most globally well-known and mostly used hypothesis test of them all, likely. If I should give one, of course I wouldn't know, I don't think anyone does, but if I should give my best qualified guess on the mostly used statistical procedure in the world during the last 10 or 20 years, it's still not deep neural nets. In a few years it might be, but it's still the two-sample t-test. The example, the nutrition study example, we emphasize again the hypothesis that we are about to test is the hypothesis of no difference between the two means in the two hospitals. I give that the name delta I. There's a typo here, it should be the alternative there, H1. If I want to emphasize, we have this classical non-directional alternative. We did mention last time that the world sometimes has non-directional alternatives, but we don't discuss those in our course, so don't think about that in our class. It's not like we suddenly throw something else in your faces. So the non-directional alternative is the mostly used. Then I have to find the t-test statistic. I plug in the two means, I plug in the two standard deviations, and I do hand calculation, or I use my R to find this number. I find that it's around 3. Now, before we look at the actual results, what would a t-test statistics around 3 sort of indicate to us? Just in our gut feeling. Now I've shown you also here, if I plug in the standard deviations here and the variances, I get degrees of freedom 16. That's no coincidence that I get 16. It basically corresponds to 9 minus 1 plus 9 minus 1. In some cases, that's where we end with this complicated degrees of freedom computation. In other cases, it will be smaller. But 16 is a pretty classical place to end. Back to my question. No cahooting, just gut feeling. I have a standardized difference of around 3. What do we expect from a t-test statistic? Is that typically large or typically small? Just gut feeling here, no clear answers. How many think it's small? How many think it's large? Good job, guys. So it helped a little bit with the previous question there. I would expect 3 is large because plus minus 2 sort of roughly. 2 is roughly the limit between large and small, at least if we use the classical 5% way of thinking, right? And at least if the n is not too small. So maybe a little more than 2, but 3 seems pretty large. Let's see if we are right. Let's check. What's in the t-distribution? What is the probability? The 16 df t-distribution, what is the probability to go beyond 3.01? That probability apparently is only 0.00415. I see that by plugging into the PT function. PT is the probability distribution function of the T distribution with degrees of freedom. You can plug in non-integer degrees of freedom. The function knows how to deal with it. This is PT is the probability of being to the left of 3.01. That's the definition of the P functions. So if I want the probability to be to the right, I say 1 minus PT, right? And that's why I read off this number, and then I multiply by 2, because the definition of the p-value is that you should multiply this by 2. Because extremeness can be in both ends of the scale, and it's symmetric, so we can multiply by 2 to have both of them counted in. So the p-value is what we've already seen in the beginning, a pretty small one. Strong evidence against the null. So there is a difference. And we can allow ourselves to observe what the difference is, which has the higher load compared to which has the lower load. So we can say that the hospital B nurses have a larger mean energy use than hospital A nurses. That's two-sample t-testing. Oh, it's going well today, at least from my side. Let's see. I need some music. Good job. Good job. Now we are getting there. Small p-value, we reject. We have evidence against the null. Having evidence against something means that we don't believe in what we have evidence against. That's the meaning of the words. And not evidence for, which is the opposite meaning. Good job there with the fingers. One more thing before, maybe 2 more things before the break. This was hypothesis testing.